Well, hello, AP Statistics students. Looking at mock exam number 2, question number 1. This question was on a previous AP exam, and my friend Jared Derksen had a couple edits to make it a little bit longer, more similar-esque, to the AP exam this year. And you might recognize this as one of my favorite match pairs designs. We did talk about this back in chapter 4. But back in chapter 4, we did not do really all the parts. I had to leave out certain parts that were on the original question, which you'll see on questions A, B, and C, like asking about identifying inference procedure. This is a really good question, not only assessing your knowledge of match pairs designs, completely randomized designs, but also how to randomly assign treatments, as well as what inference procedure. So this is kind of doing chapter 4 about sampling and experiments, combining it with what you know about inference and significance tests and stuff like that. So this is the 25-minute question, the first question. Probably a lot of writing that you have to do on that first question, a lot of typing, as it were. We have 100 randomly selected people. So randomly selected people who are going to participate in this study, and they're comparing a new compound with a current compound to see if the number of mosquito bites on the arm is less from the new compound compared to the current compound. So if the new one works better, then the mosquitoes should bite you less. We also have up to 100 bins with an equal number of mosquitoes in each bin available to use in the study. I guess that's important. You could be asked, like, why is it important that there's an equal number of mosquitoes? That's a form of control. You don't want the new treatment to have bins with 1 mosquito and the current treatment to have bins with 1,000 mosquitoes. You'll obviously have a lot more bites if there are 1,000 mosquitoes. So this is an important form of control, to have the equal number of mosquitoes in each bin. Maybe I should have added that to that question, to this question. That would have been smart. But anyway, suppose this study is to be conducted using a completely randomized design. Describe a randomization process and identify an inference procedure. So this is 2 parts. So make sure you answer both parts. You have an and in here. Sometimes they'll underline an and if they're concerned students might miss out from doing both. So a completely randomized design, we're going to have our 100 people. And we have our 100 bins, so that seems nice. So completely randomized design, you start with, I'll start with a diagram. A diagram isn't sufficient in and of itself, so I'll have to use words to explain this. But we have 100 people. We have our 100 randomly selected people from a certain state. And then probably the most important that students will forget is mentioning we will randomly assign, which specifically this question is asking you, how will you randomly assign? What process will you use? So we have 100 people. We're going to randomly assign them to one of 2 groups. We'll call it group N for new, and group C for current. We'll make sure there are 50 people in each group. That's not a requirement in experiments. It's beneficial, it's nice. It can increase the power of the experiment if you have an equal number in each treatment group. However, it's not required. Sometimes students think it has to be 50-50 and then they're at a loss. Like, what if you have 25 people? Like, you can't do the experiment with only 25 people. You gotta split someone right down the middle, like Solomon or something. So then you have your 2 groups. You're gonna, for group N, you're gonna apply the new compound. For group C, we'll apply the current compound. And then we will measure, or I guess we'll let the mosquitoes feast. So then we'll count bites, and then we'll compare. And we'll see, is there statistically significant evidence of a difference between the 2 groups? So when you have two groups like this, you have one quantitative variable, two groups. You might imagine it being like, not that you have to include this part, but here's like the new, here's current, here's number of bytes. Maybe if the new is better, there'll be a lot fewer bytes. And maybe current's way up here. And it doesn't have to be normally distributed, but so it could look something like that. When you have a dot plot like that, or a box plot, histogram, whatever, comparing one variable in two groups, that would be a two-sample t-test is what we would use. So that's the inference procedure, is a two-sample t-test. To answer the question, though, like I said earlier, the diagram isn't sufficient. So you'd want to say, we'll have 100, so just make sure you hit each of these. We're going to take 100 people. We're going to randomly assign them. Now we have to elaborate on that. So maybe we'll elaborate on that down here. And really, I guess this question just says describe a randomization process and identify the procedure. So it doesn't ask you to design the whole experiment, but I thought since we're here, let's just talk about it, how you would do that if you were asked to design the experiment. You have 100 people, randomly assign them to two groups of equal size. One group, you'll apply the new treatment on the arm, count the number of mosquito bites. The other group, you'll apply the current and then count the number of mosquito bites, and then we compare the number of bites for both groups. But how would we randomly assign them? I find that probably the easiest way to describe is the names in a hat. So what I mean is this. We'll have 50 slips, 50 equal sized slips with C on it, and 50 with N on it. We'll let the 100 people select one slip from a hat after we've mixed them, of course. The slip they get will be the group they're in. C or N. Now I hope that using C and N isn't too obvious. You'd want the people to be blind, right? Single blind is if either they don't know what treatment they've received or the person who's measuring their number of slips doesn't know. So I hope that using C and N isn't too obvious to people. You could always say A and B. A is the current and B is the new. You don't have to use C and N. But on single blind, the people themselves wouldn't know what treatment they're receiving, or, important thing here, or the people who are like counting the number of bites wouldn't know what treatment they received. So if one of those groups don't know, it's single blind. If both of those groups don't know what treatment they received, then it's double blind. So there's some confusion about single blind. A lot of times we think single blind's only the people who receive the treatment. They don't know. But maybe you could still have a single blind experiment where the people themselves know what treatment they received, but the people interacting with them, measuring their response, that they don't know what treatment they're receiving. Okay, so if this were scored, one main thing that we'd be looking for is that you mention that you're mixing. It has to be random, right? Randomization process. You have to be mixing the slips. The other thing that's important to note, which I've kind of run out here, this is the person or the subject does not put the slip back in the hat. That's important that it's without replacement. So there's other ways that you could randomize the treatments. You could number all the individuals, use a random number calculator to randomly select 50 different numbers. Make sure you have different numbers. And then those 50 numbers will receive the new treatment. And then the remaining 50 people who weren't selected will receive the current treatment. That's pretty easy to say too. I would encourage you though to say that they're different numbers. And potentially if you have multiple groups, you want to say, like, we've selected 50 for this group. So say you have different levels of your factor, of your explanatory variable. If you have different number of treatments, more than just 2, then be careful to talk about, once we've used up those numbers, those first 50 numbers, we're not going to use those again. So the problem with a random number generator, if you use it multiple times, is it could give you the numbers that you had earlier. So you have to clarify that and be really good in your communication. Okay, so I think we answered that. We have our inference procedure as a 2-sample t-test. And then over here, we talked about the randomization process. Everything out there in black is just extra. Suppose the study is conducted with a matched pairs design. Describe a randomization process and identify an inference procedure for this study. So let me draw a picture again for matched pairs. We would have our 100 people. We're going to randomly assign them to one of 2 groups again, N or C. We're going to do the new and counts. This is abbreviated. This is do the current and counts. And then we switch the treatments. Now we do C and new. They get the current, and then we're going to count. And then we have the new, and we're going to count how many mosquito bites. And then we're going to calculate and compare the difference in the number of mosquito bites. Now, rather than maybe doing it sequentially like this, you could use both arms, right? So maybe you do the new on the right arm, and they get the current on the left arm. And then they would get the current on the right arm and the new on the left arm. So you don't have to draw a diagram like this, but the important part is that you describe the randomization process. So we have 100 people and we have 100 bins. So it sounds like we will have to have both arms in a bin. I hope that that's possible with the bins, that like there's like 2 doors to put your arms in at the same time. So we would say, since one person's going to do both treatments, since one subject will receive both treatments, one treatment per arm, we will flip a coin. Even say that it's a fair coin, flip a fair coin. If heads, the new will go on right arm. If tails, then left arm. The other treatment, or the current, I should say, the current formulation will go on the other arm. Both arms will be placed in one bin. I hope this is possible to do that. It was kind of unclear from the question, like how big is this bin? Can you put both arms in the bin at the same time? Okay, so that was our randomization. So mainly we have this flipping of a coin, and it's important. You don't want to put the new formulation on everyone's right arm. The majority of people, 90% of Americans, I think, are right-handed. So maybe the right arm, since we use it a lot more, maybe it's more muscular. So we don't want to put the new formulation on the right arm. And we don't want to put the old formulation or current formulation on the left arm. That's because maybe it's harder for mosquitoes to pierce the skin because you have stronger muscles on the right side of your body if you're right-handed. Maybe it's easier for mosquitoes to bite you on your left arm. Maybe there's some other difference between your arms that we don't really know, like how to control for. So that's the importance of, hey, we're going to address that by flipping a fair coin. And it should be like roughly equal numbers of people who have the old on the right versus the old on the left. That's the importance of randomization. That's an important feature. That's definitely a question that you could be asked, like why even randomly assign in a matched pairs design. And that's one reason why that would be important. And it is a matched pair, so the inference procedure that we'd use is a paired t-test. Is our inference procedure. You don't really have to do anything with that, but that's our paired t-test. So I do want to mention, maybe let me write it in green. If you're asked for hypotheses for this first question, the hypotheses might look like this: mu new minus mu current equals 0 is your null. And your alternative would be mu new minus mu current. And we think the new might lead to fewer bites, so less than 0, where mu is the unknown mean number of bites for the given treatment. That's another, probably I would guess, another good guess for what type of question you could be asked. Not only identify the inference procedure, but identify the hypotheses. Whereas this question, for a paired t-test, you would have the null would be the mean of the difference, new minus current equals 0. Notice we only have one mean, really important. With two sample t-test, we have two means. With a paired t-test or just a regular one sample t-test, we have one mean. Mu n minus c. And if the new is fewer, so fewer bites, you could also define it as mu diff. We've used that in our notes before. As long as you define the difference as like n minus c or c minus n. So that was a little bit of extra stuff. We've kind of alluded to the answer on part C a little bit. Which of the designs, A or B, is better? Part B is better. For testing the effectiveness of the new compound versus the current compound. B is better. It's best to control for person-to-person variability. Some people may attract mosquitoes more than others. Mosquitoes more than others. So to reduce the variability of our statistic, we'll control for this by having each person do both treatments in a random order, or at least which arm receives the treatment in a random order. Okay, so If you look up this question online, you can see the College Board solution. It ends there, A, B, and C. But to make this a 25-minute question, here are some other things. Whoops. Here are some other questions that you answered. If the scientists used a completely randomized design from part A, describe an appropriate graphical display that could be used. So like I did before, you can imagine you're going to have the number of bytes as your response variable, and you're going to have to compare the two groups. So maybe you could have something like that. You have a lot of people here. So with 100 people, 50 per group, it might be justifiable to do comparative box plots. Or maybe you'd have a stem plot. I don't know what the numbers would necessarily be. So this would be the new, this would be the old stuff or the current stuff. Something like that. To compare them, you'd obviously want to have a key. Now, you weren't actually asked to make a graph, but I just want to connect this with graphs that you've seen and what it could look like. So describe an appropriate graphical display. You could do comparative box plots. With number of bytes as our variable between two groups. So comparative box plots, comparative dot plots, comparative stem plot, back-to-back stem plot, comparative histograms, any of those would be legitimate ways of comparing this data. If the scientists use matched pairs, write appropriate null and alternative hypothesis that would be used to find any parameters. So earlier we actually answered that. For a matched pairs design, we would have mu diff equals 0, mu diff is less than 0. I will define diff as the new minus current. If new is going to work, there'll be a smaller number minus a bigger number. So that would be a negative number if it's working well. You could very easily switch current and new. You'll just have to be careful to switch your inequality sign to be greater than 0 if you did current minus new. Now, if you left it like this, you wouldn't get full credit. You have to define the parameter. Whether you're asked to or not, you should define the parameter. So mu diff is the unknown mean difference in number of bytes for the new formulation minus the current formulation. Tips and keys about defining. Make sure you mention mean and difference. That's not a difference in means, plural, but it's one mean difference. And make sure that you have the variable that you're measuring. It's really helpful that you say something like unknown or population or actual or true, as long as you don't say it's the sample mean. The sample mean's X bar. This is the population mean, mu. So the unknown mean difference in number of bytes for the new formulation and the old formulation. And then next we have continuing with the matched pairs design from part B. The scientists found a p-value of 0.023. What is their decision and conclusion? We'd say since 0.023 is less than 0.05. I don't know if they, I guess I should check. Did they mention a certain alpha level? It doesn't look like it. Okay, so we would reject HO, and we have convincing evidence that the new formulation, well, let me say it this way. Based on the hypothesis that we just wrote up here, that the mean difference in bytes, new minus current, is less than 0. That should be sufficient, but in other words, we would say the new formulation appears to help reduce the number of mosquito bites. The reduced number of bites compared to the current. And since well, let me answer the next question. Based on the p-value that we just had, can the scientists conclude that they have evidence that the new compound caused the mosquitoes to be repelled more frequently? We'd say yes, since they randomly assign the new or current treatments to subjects, we can infer the cause, which is the treatment, led to the effect, which is fewer bites. You shouldn't mention the random sample aspect here. The random sample would let us generalize to the whole population from the sample, and that's not what this question's asking. So if you mentioned on your response that, like, yes, we have a random sample and random assignment because you're not really sure which one really applies, that would probably get a partial. And I hope you can respect that, because students need to know what was it about the experiment that allows us to infer cause and effect. It's not the random sample, it's the random assignment that allows us to do that. A lot of experiments have volunteers, and that doesn't mean we can't infer cause and effect. That just means when we infer cause and effect, we can't expand it to a whole population. We can only generalize then to people similar to the volunteers in the study. So I would guess if this type of question appeared, you would definitely want to answer the question, say yes or no, and you should mention the random assignment. It's also really beneficial if you mention the treatments in context. It's really important to mention that. And then I do want to mention up here, make sure that you make a statement about the null. Make sure you compare the p-value to the alpha level. Make sure you mention that there's evidence. This isn't proof that it works, but we have evidence, strong evidence, convincing evidence. We have evidence, statistically significant evidence, that the mean difference in context is less than 0. This is evidence. We could have made, at the alpha of 5%, 5% of the time we're going to make a type 1 error. The probability of type 1 error is alpha. So it's just evidence. It's not proof. Maybe we do a follow-up study, different group of people, maybe a larger sample size, maybe more mosquitoes, but whatever we might do to strengthen our case. This is not proof, but it's evidence that the new formulation leads to fewer bug bites on average than the old formulation. So this question, kind of taking a step back and looking at it all, quite a few different aspects here. We have cause and effect from our chapter 4. We have concluding a test with a p-value. We have a matched pairs design, which we did kind of in chapter 8, chapter 9. We have something from chapter 1, like how do you compare this data? We have to make a decision and explain why is it better to do a paired design. and then describing randomization process and inference procedures. This, I think, is an excellent question, an excellent example of what the AP exam this year could look like. If you'd like more details about what answers A, B, and C might look like, you can check out, I'm not sure I'm able to circle up there. You could check out the 2005 Form B. You can look that up online and check out the scoring guide. But again, parts D and following were additional questions to make it a 25-minute question like this year's exam. Thank you for watching this video. If you like the video, give me a thumbs up. Give me any comments, feedback by email. And thanks for watching. Hope you have a great day. And thanks again for all your hard work to prepare for this year's AP exam.